Thank you everyone for joining today. This is part of the Sydney Physics Dialogues, and today is all about quantum information science. So I'm Stephen Bartlett. I'm a professor in the School of Physics and Sydney Nano and the ARC Center of Excellence for Engineered Quantum Systems. I'm a quantum information theorist. What I'm going to do today is just give a very brief, like less than 10-minute overview of what we're doing broadly within the quantum information science group in the School of Physics, and introduce the different labs and different research areas. And then we'll hear from some of the academics from each of those areas about what's actually going on. And we're not even going to cover it all today. At the same time next week, we'll have a follow-up session with some more discussions of what we're doing. So thanks very much for joining. We've got John Bartholomew monitoring the chat at the moment, and you can type in your questions there, or you can just shout out if you have an urgent question, and we'll see if we can answer things. Okay, so as I said, I'm going to start with just a very, very brief overview of quantum information science, what it is and who we are. So what is it? Quantum computing and quantum information science, quantum information science is a bit broader than quantum computing, but the lens of quantum computing is really providing a focus for many of the developments that we're doing in this area. It's really trying to figure out how we can use the laws of quantum physics to build better computers, better information processing devices. And this is inspired by some theoretical ideas that suggest that a computer or an information processing device that's built out of quantum systems is actually going to be a lot more powerful than a conventional device. So that's fantastic. That's the promise. The challenge for the physicist is how can we make a very complex device like a computer that still operates quantum mechanically. So we normally think of quantum mechanics as applying to things that are very small, microscopic, and we want to make a very large object like a computer with many, many, many individual parts. And we don't normally see quantum mechanics act on that scale. And that's because quantum systems are very fragile, they're very prone to errors. And one of the main challenges is for the physicists trying to scale up quantum systems to the macroscopic level where we could actually build devices out of them. And that's starting to happen. We have quantum computers now in the world and in the School of Physics at Sydney. They're very basic devices, only a few qubits, but it is demonstrating that the idea has some legs, that things can work. So it is still early days in the development of the hardware, but we really get the feeling in the field that right now, really this year, these few years, we're at an inflection point, and the next few years are going to be absolutely amazing for the development of the technology. And that's going to let us do all sorts of interesting science. So I'm just going to try to give a super brief idea of how quantum computers work. And it's a challenging one to convey. But you have all heard of Heisenberg's uncertainty principle, the idea that in the quantum world, we can't know everything about a quantum object. And the more we learn about one thing, the less we learn about something else. Well, the idea with a quantum computer is that we want to force that uncertainty we have, the fundamental uncertainty we have in a quantum device, to be about what is the computational path that that computer is doing. So we're very uncertain at a fundamental level of exactly what's being computed. So you're sort of thinking many quantum computations are being done simultaneously in some sense. And then at the end, we want to use quantum interference to amplify some of those computational paths, to suppress others, and to give us an answer that combines those different computational paths in some way. So that's a bit of a vague explanation, but you can sort of see how some of the rules of quantum mechanics might allow that. What's really going on in a quantum computer is a bit of a mystery. The mathematics is clear. but at a fundamental level, even those working in the field feel a bit uneasy. And that's similar if any of you have studied Bell's theorem, Bell inequalities, and trying to understand entanglement. It has that same sort of property. You look at the maths and you're like, oh yes, that's what quantum mechanics predicts. That's what we see in experiments. But what's really going on is a challenge to understand in terms of our classical concepts. I'll be very brief here, but there's huge fundamental questions about what we can do with such a quantum computer. So I said it's very likely to be more powerful than the computers we have today, but only maybe at certain tasks, and we really don't understand exactly what those things are. There's a whole range of things that we believe quantum computers will be very good at, and a lot of those are problems in physics. So understanding how materials work, understanding how quantum materials work is something that a quantum computer should be very good at. It's likely we really won't know the answer to some of these questions until we build larger quantum computing devices and start to play and hack with it. So that's a bit of an introduction to the very broad questions we're asking in this field. And now let me just take a couple more minutes and tell you a bit about what are the different research areas in the School of Physics at University of Sydney that are pursuing these directions. I'll introduce these teams and then you'll hear some more details as we go over to our other speakers. So we have a very huge experimental program in the school. At the moment that consists of 3 labs. If you look down in the bottom corner, I say the Sydney Nanoscience Hub. So that's a building. Sydney students will be aware of that, a fantastic new building, and all of our quantum groups are located in that lab. We have the Quantum Integration Lab, and John Bartholomew is going to tell you a bit more about what's going on in that lab today. We have an enormous collaboration between the Quantum Nanoscience Lab, led by David Riley, and Microsoft. So Microsoft is one of the big players in quantum computing. And along with their effort in the US, they've sponsored a couple of university labs around the world to really push on developing quantum technologies in a partnership between academic groups and Microsoft. And one of those places is Sydney. So students working in that lab get a chance to work with Microsoft engineers in really building some amazing devices. We also have the Quantum Control Lab. So Cornelius is going to tell you a bit about that next. So that is trapping ions and using those as quantum devices. There's a nice picture of a very complex laser system that they use to control those ions. Along with the science that's going on in this lab, a great success story is the spin-out company Q Control that has really originated from that lab. So that's the experimental program at Sydney out of those 3 labs. And you'll also hear a bit today about the theory program. So we have quite a large theoretical effort looking at quantum information theory. And some of the very broad questions that we're asking are what are the key properties in quantum mechanics that really let us do something more powerful than we can do with a conventional computer? What are those properties? Is it entanglement? Is it superposition? Or is it something else? We're very interested in how we can construct quantum error correcting codes to protect information in the presence of noise and faulty parts to make things work on a large scale and quantum mechanically. And we're also very interested in new exotic materials and theoretical structures that are going to enable those quantum technologies. And you'll hear a bit more about our theoretical program from Isaac Kim today. So my final slide here is just to sort of highlight some of the environment that we have at Sydney. So not only the groups that I've just talked about here, but we're part of the ARC Center of Excellence for Engineered Quantum Systems, which is an Australia-wide center that involves several universities, and we're developing technologies for quantum information processing. We're also very happy to be part of the Sydney Quantum Academy, which offers all sorts of training programs for undergraduate and PhDs. It's just getting started this year, but I'd encourage you to look into that a bit further if you're interested in a research career in quantum mechanics. Okay, with that, I'll pause. We can take a moment if you have any questions for me before I hand over to the other speakers. Any questions? All right, so why don't I stop sharing my screen and I'll let, who's next? It's Cornelius, isn't it?
That's right. Okay, well then, without further ado, I'll just get started, and I'll be talking to you today about trapped ions for quantum information processing, which is a very clunky way of saying, how do you build a trapped ion quantum computer? So that's what I'm really going to show you. And as Stephen already outlined, so this is the building that you can see on the right here. I think I can even get a laser pointer. That's the Sydney Nanoscience Hub, so one of a very new building that was purpose-built to house both lecture theaters and specialized laboratories. And I'm representing the Quantum Control Laboratory. And to get started, I should probably set the stage first. You may not have encountered very much in quantum yet, and so I'd like to start out by telling you what is a quantum bit actually. And so you all know very well the classical bits. So that's my standard example, the light bulb. There's a 0, there's a 1, so that's binary logic, hence the name binary digit or bit. And you'll find those everywhere. I mean, you can either consider just a capacitor where you can store charges, and then the voltage will be at a certain level, so that's your 1, or at a lower level, that's your 0. And if you get very fancy and you integrate them, you can build these DRAM chips, so basically the memory in all the computers, in all the devices effectively that you're currently using to attend this talk will have this built in there. So those are the classical bits with 0s and 1s. Now, what's a qubit? Generally, when we talk about qubits, we like to have some pictorial representation. So what you can see here is what's called the Bloch sphere. So you can think of just the Earth, a globe, a sphere effectively, that we use to represent the qubit. And then to make that analog from the normal bit to the classical bit to the quantum bit, we can associate again a state called 1 at the bottom at the south pole, and the north pole is our 0 state. But one peculiarity here is that we can also be at the equator. And so this now is a state that you would write in quantum mechanics like that. So it's a superposition. It's effectively a sum, a weighted sum of those two states. So simultaneously 0 and 1, or in this particular mix. That's the specialty of quantum bits. And the important bit is that these are complex numbers that are normalized. You also sometimes see those represented as spin up or spin down. So you'll hear the word spin sometimes, also for qubits. And that's actually one of the two key ingredients in quantum computing: superposition and entanglement. So for a single qubit, you can see the superposition right here. That's just those two states. And if you have more than a single qubit, then you can actually entangle them. That's a much more powerful correlation that has no classical equivalent. And to continue now, I should tell you, where do we find a qubit? And me being trained as an atomic physicist, the first thing I do is I look at the periodic table. So I've plotted the table down here for you. And the ones that we really like are those. So those are actually the elements that when you photoionize them, so these all have 2 outer electrons, and when you photoionize them, they become hydrogen-like. So there's just a single outer electron remaining, and that's why we're calling them singly charged ions. And so those are used around the world to build trapped ion quantum computers. And at the University of Sydney, we're using beryllium and yttrium. So one very light ion and one very heavy one. Now, we found ourselves a qubit, so you can encode this object somehow in this atom. But how do we store those? So those charged particles need to be stored somewhere. And you can see those 2 kinds of traps here. Those are common traps that you'll find for ion trapping. So one is called the Penning trap, actually not invented by Mr. Penning, but by Hans Demel instead. And then there's the Pole trap, named after Wolfgang Pole, who invented that. The difference between the two, they look rather alike, wouldn't you say? But the difference between them is that the Penning trap has a magnetic and an electric field to store charged particles, whereas the Pole trap does that only with electric fields. And so just the invention of these 2 traps was awarded the Nobel Prize in 1989. And those are basically the workhorses that we use for trapped ion quantum computing. Now, the next important ingredient is laser cooling. you probably haven't really heard about this or are not familiar with it, that you can use light to cool. So you can, in fact, if you have a laser, and that's the thing that you can see on the left, that's the same picture that Stephen Bartlett showed earlier. If you have laser light and you've got a device that contains your ions, in this case, that we want to cool, you can use well-timed forces. And well-timed forces, this is the example here. If you have a child on a swing, if you want to decelerate, and effectively cooling means deceleration, you want to take out motion, kinetic energy, then you need to push the child at the right time, right? Otherwise it would slow down or would speed up. So how do you do that with light? Well, the key thing to understand is that light, a laser beam, contains photons. So it's many, many photons that we're looking at. And each of these photons has a momentum, so h bar k that's given here. And if a photon hits an atom, it can be absorbed, but the momentum doesn't get lost, it's conserved. So if the atom moved one way, the photon went the other way, you can effectively slow it down. Now, the key, though, is you have to avoid accelerating it, because after all, we want to cool it, right? And so what you can use there is another effect that you've certainly heard about in physics, and that's the Doppler effect. So when you're looking at a spectral line that is characteristic of an atom, so if you send a laser beam to it, it can absorb light at a certain frequency, that's what you can see here. That's the line shape. This gets broadened, and this broadening is called Doppler broadening or Doppler shift here. And by tuning the laser to the appropriate position, we can actually use that to slow it down. So every absorption of a photon slows the atom down, and so it becomes slower and slower. And this works really well because if you consider that we have this apparatus here and the trap here that sits just above room temperature at about 300 Kelvin, the ions, these elements that we're using, these atoms actually come out of an oven here at the bottom. Those are tubes filled with little shards of metal that we heat up. And so when this material emerges there, it's hot. It has 600 Kelvin. Yet when we turn our laser cooling light on, we can cool those down to half a millikelvin. So that's far less than actually lots of the fridges that you hear about, or dilution refrigerators that you can see for superconducting qubits. It's really cold, so 0.5 millikelvin. That's the operating temperature of these ions, albeit they are in this room temperature vessel. Now, this is just a generic picture that will illustrate how this works. You have the ions in their traps, so they are just represented by those balls in the middle. And then this is the first image of a quantum byte. So these were 8 qubits or 8 ions trapped here. The image quality has since improved a little bit, so it looks like that. And then when we run those computations, it always starts with a cooling cycle. Then we have quantum operations and then a detection. So in which state are these ions? And then we repeat this. And that's what it looks like. So if you were to watch this quantum computer in action, that's really what it would look like. But in order to make sense of it, we actually capture with this camera here individual frames. So the outcome of each repetition gets captured in an image, and then we can turn that into the good old binary that we have here. And if we then do statistics on it, we can get these coefficients up front here, and they encode the answer to the question that we asked. So now I've shown you a lot of illustrations and diagrams of how things work, but what you really care about most likely is what it looks like in practice. So let's take a quick walk into our lab. So this is at the Sydney Nanoscience Hub, and we are walking past our preparation room. That's where we built those devices, and straight into the main Terbium lab. You can see danger warning signs everywhere because we have laser beams. So that's also why there are no windows. Now we're going inside through these sliding doors and welcome to the first experiment. So this is an ion trap. It's actually a quite small vacuum vessel. So let's look at here. That's one that we use for quantum sensing. And then in the middle, there's a table with lots of optics. And you can see there are a lot of optical elements and fiber optic cables. That's the yellow ones and the blue ones here. They're shared between these experiments. And when we now continue walking over to the third table, there's another experiment here. And this big thing here is an objective looking inside there, and lots of classical computers. Because in order to control all that, you need classical computers, classical electronics, microwave generators. So there's a whole lot of equipment, and always in these kind of systems and setups, more optics. So the lab that you've entered right now houses our Pole traps for quantum computing and simulations. And you've seen that image here on the left. That's this objective that I was briefly talking about. And if you were to take that off, you can actually look inside and see that ion trap. And in that middle bit of the trap here, so the trap is maybe a centimeter or two across, But in the middle here, that's where we trap our ions, and that's an image that the camera would take. Here's some numbers on the right. There are technical details, but basically what that is saying that we have a very long coherence time in our qubits, so we can really do many operations, and those operations have a rather high quality. So those are technical details. We've got another lab, and that's the penning trap lab. So remember those two kinds of traps that I talked about. Looks quite different. And what you can see here on the left is a 2 Tesla superconducting magnet that we use to create this magnetic field that we need to actually trap the ions. And the difference was that in the previous one, I'll just go back briefly, you see that we have a few qubits lined up in a string. Now in this penning trap, we can have many hundreds of ions in large lattices. But the operation is much more complicated and takes high-powered laser systems and also cryogenics. So what does that lab look like? Let's take a quick look. So this is this 2 Tesla magnet that I just mentioned. You can see again an image of the trap there. The cameras used for detection. And again, you need computer control. And here it's actually quite a sophisticated control. And you can see an image of these many ions there on the screen. Electronics, classical electronics are needed again, plenty of them. So are computers. And then now we're walking around this table to where the light is actually produced. And I mentioned high-powered lasers. That's why there are boxes here, metal boxes, and everything is closed, and warning signs all over the place. And then that light that's being produced there is actually converted twice. So we're turning infrared light to visible red light. And then what you can see in this video is the ultraviolet radiation that we then send to those ions to control them. So this is that other lab. And now that I've shown you, at least in brief, what it is that we do and how we do it, let me say a few words about, if it advances, a few words about what we do and what we are working on. So it's the Quantum Control Lab, and hence we're also working on quantum computation. And when thinking about quantum computation, a helpful way is to look at this scheme here on the right. So this is taken from this paper down here, where we're looking at the physical qubit hardware. That's how you make qubits, how you actually physically build a quantum computer. But then you need those classical control pieces. That's this level here that you've seen a lot of cables and devices there. But then is the question, how do you use those to control your qubits? So that comes down to hardware characterization. So does the hardware do what you want it to do? There's feedback and stabilization. So sometimes things don't really work. So you have to always calibrate them and follow errors. You also want to suppress errors. And then on top of that is quantum error correction, which we'll certainly hear more about from the theory group, which is when you have a roughly working physical system, how do you bring that together to build a fault-tolerant quantum computer? Because who wants a quantum computer that doesn't work most of the time? So you want something that is reliable, and that's where error correction comes in. And then on top, you have algorithms, the user interface and such, and that's when you see diagrams like that, that's a circuit diagram. And bridging this to that, to the actual hardware, that's where we come in. So this quantum firmware here in the middle is really what the quantum control is about. And to give you an example of what that means is, let's think about a rotation error. So we wanted to go from the 0 state up here down to the 1 state at the bottom. And the problem was that this is what's called a pi pulse. The problem was that we went too far. So either it was miscalibrated or the device didn't really work as well as it should. And so we have an over-rotation error. And one easy way to fix this is to not just do a single pulse that takes us around, but instead do a composite pulse sequence. So you can see this here. These are 4 pulses. They have a specific duration and a phase. So that's how they are calibrated and they're in the phase. And I'm illustrating this here for a pi on 2 pulse. So we're only going to the middle so you can see much easier what happens. We wouldn't make it all the way, but thanks to this pulse sequence, we're actually doing an extra loop around here. So that at the end of this, we're getting where we want it to be, even though the gate itself was not calibrated correctly. And so this is the kind of thing that we're using to bring down error rates. And this is taken from a 10 qubit register that we have in the lab, where we're looking at error rates. And red is when you don't do any of these error suppressing techniques, and blue is the error rate when you do them. So we homogenize the error rate across that register, and it's actually quite low. So this is just an example of some of the techniques that we're using. The other focus that we have in the lab is quantum simulation. That was also mentioned in Stephen's overview as part of the applications. So simulating quantum systems, and how better to do it than by another quantum system that mimics the first. And so you've seen the penning trap briefly with these large crystals. That setup is being built mainly to look at mesoscopic simulations of quantum magnetism. So if you want to understand how phase transitions occur in lattices in large crystals, or how, for instance, superconductivity works at a fundamental level, then that's a system in which you could study this. In the pole trap on the right, where we had these shorter crystals and just strings of ions, we're currently looking at chemical dynamics. So understanding how molecules react with one another, how changes occur. And if you've heard about the Born-Oppenheimer approximation, that's what generally you do in chemistry to freeze out motion. We try to go beyond that by using a quantum system to do this. So with that, I'd just like to introduce the team and thank the team, actually. So there's myself and Robert, who lead the individual labs, and obviously the group itself is led by Michael Wiesek, who's also the co-founder of and CEO of Q-Control. We've got a few postdoctoral researchers and graduate students, and certainly room for more. So if you're interested in honors, MPhil, or PhD, please get in touch. We certainly have room for more people. And that was it on my end. So I'm happy to take questions if there are any right now.
Thanks, Cornelius. We have one question from the chat, which I'll share with you. So the question is, are you detecting single photons? And if so, how are you detecting them?
So we generally detect more than a single photon. We have single photon counting devices, so avalanche photodiodes. So we could theoretically detect single photons. But luckily, these ions, when we detect, we can do what's called a quantum non-demolition measurement. So we can actually measure for longer and we won't alter the state. And so we get many, many more photons. And that helps us because these cameras that we use to look at many of these ions, they're not that sensitive. So even though you might have a single photon sensitive detector, there are mirrors and other optics in between, so you don't get all the photons. So luckily, we can detect more and more. All right.
And there aren't any other questions in the chat at the moment, but I have a question that I think that people might be interested in. You showed some of the labs. Do you want to tell us a little bit about some of the special features of the lab? There looked like there might be some special features.
Indeed. And in fact, I can answer that question directly if I share my screen again. So the labs are actually quite special. So they're what's called Class A labs, and you can see it cut through here on the left. So that's this ytterbium lab. And if you look at the temperature specifications and the humidity, you can really see that they're quite something. So the complete air in this lab gets replaced every 68 seconds. And then these sliding doors, in case you wondered why we had them, there to maintain air pressure so that you don't have pressure waves when the doors open. Then the entire lab is shielded. So there's a passive aluminum shielding that goes all the way around and an active magnetic field cancellation system. And lastly, everything rests on bedrock. So really very low vibration environment.
Okay, great. There's no more questions in the chat, so we can probably keep going. But if anyone does have questions, feel free to post them in the chat or ask in the panel time at the end.
Is it me now?
Yep, you're up, Isaac.
Can you see the screen?
Yes, looks good.
Good. Okay. All right. Thanks everyone for coming. So my background is a theorist, and today I want to tell you about a part of our efforts in regarding the studies on what we can do with the near-term quantum computers. So these are the types of quantum computers that already exist or that are expected to exist over the next few years. So I want to just briefly reiterate what Stephen told us, which is that you might ask, like, why bother with quantum computing in the first place? And the reason is very simple. We have lots of applications if we can build a large-scale quantum computer, one being a fast and accurate simulation of the materials. And this has, if we can actually do that, this has plenty of industrial applications, because in many industrial settings, there are situations in which you want to create a material with a specific properties that you want, but in order to actually create that material, you have to go through this trial and error procedures until you actually find the material that you want. So the dream is that if you have a computational capability to design the material of your need, you can dramatically reduce the time and the resource spent on those studies. And it's not only this, but there are also other applications such as breaking crypto systems or improving the existing machine learning algorithms, which are admittedly more far apart. And also potentially quantum computers, generally speaking, do give a speed up over general optimization problems. So if we can actually run those algorithms at a large scale, this could also potentially have applications in finance. Now, it's important to put everything in perspective by learning where we're now and where we want to be. So this is a slide that I borrowed from our friends from Google, which they often use to tell people about the current state of affairs in quantum computing. So I would say most of the quantum computing hardwares to date falls into this red box region. So just to tell you like how to read this chart, in the x-axis, you have the number of qubits, which is the fundamental building block of the quantum computer. So you can think of it as like the size of the quantum computer. And in the y-axis is the error rate, which is basically the rate at which something bad happens in your quantum computer when you run a simple elementary operation. So the place you want to be is here on the right bottom end, because you have a large quantum computer with low error rate. So this is where most of the quantum computers are at. And in order to run the kinds of applications that I told you in the previous slide, the current consensus, conservatively speaking, is that this is where we want to be. So as you can see, there is a pretty wide gap between the red box and the green box. But the good news is that this better end of the spectrum for the existing quantum computing hardwares is they actually have a low enough error rate so that if we can have a sufficiently large system while maintaining this error rate, eventually there will be a point at which we will for sure be able to implement all those applications that I told you in the previous slide. And that will be really amazing. However, that's not going to happen like overnight. People need to put in a lot of effort, manpower, time, and money. So there will be this big region in the middle, which has been for a very long time be a no man's land, where not many people had a clear idea on what to do. And this concept was kind of crystallized by one of the pioneers of the quantum computing field, John Bartholomew, who coined this region as a near-term intermediate scale quantum regime. So this is a regime in which the quantum computers are large enough that it's very difficult for classical computers to simulate what the quantum computer is doing, but they're not sufficiently big enough so that we are confident that we can run a useful application. So the main challenge at the moment is to understand what can we do something useful in this NISQ regime. So what's exciting is that recently Google announced that they have developed a device called Sycamore that is capable of performing a computation that no existing classical computers can perform in 10,000 years. So this number is still up for debate, but what is clear is that they have a device which runs a certain computation extremely fast in the orders of like seconds to minutes, which would take the best existing classical computer at least many days, weeks, or months. So that's a big accomplishment. And more importantly, that happened, that's just at the beginning of this NISQ era machine. So you can sort of imagine the power of the devices that will appear in the near future if this is what occurs at the very beginning. And moreover, this didn't happen like 10 years ago or 20 years ago. It happened last year in 2019. So this current consensus is that at least, very conservatively speaking, there will be a time, at least 5 to 10 years, I think some people even say like multiple decades, in which we will basically play with all sorts of quantum computing devices which are presumably going to demonstrate superior performance over this Google's device. So that means there's plenty of opportunity, and we don't know what's going to happen. But you could be the part of the story. You could be the one who determines what's going to happen in this era, and that's one of the things that I'm interested in doing. So there's a lot of debate on whether there will or will not be any useful application in the NISQ era, but I personally believe that there will be one. And today I want to briefly tell you about the reason. So this will give you some background. Already, let's say 5 years ago, people came up with some interesting ideas on what to do with these near-term devices. And I would say the motto behind these approaches is basically, let's try something with these near-term quantum devices and see what happens. The underlying idea is very simple. So suppose you want to simulate some quantum system of interest that is classically intractable. What you do is that on a quantum computer, you let the quantum computer does what it does the best, which is to create some quantum state by applying some gates and doing some computation. Now, what the kind of state that you create that way will generally not be the kind of state that will appear in nature, but perhaps you can control the state of the quantum computer by sort of measuring the physical quantities of interest, such as energy, and you change the parameters of the quantum computer so that you can lower the energy effectively. So you repeat this process many times until you hit a low enough energy, which you expect to be the ground state, at which point you can study many interesting physical properties of the system that you otherwise cannot predict. So it's a very attractive paradigm, and it's good in the sense that it's very easy to implement. But in recent years, people have studied these approaches very seriously and found some challenges. One of those challenges is that the existing quantum computers are not perfect. There are some decoherences and imperfections, and also the existing quantum computers are somewhat small. And both of these things will improve in the future, but the current state, the state of affairs, is that these things seem to be insufficient, so that you can just run these naive version of these early proposals and hope to achieve some form of quantum advantage. However, there are some good news, which is that now people started more seriously to think about more seriously on what to do with these devices, and came up with methods that are more based on the physical intuitions that we have learned about the systems that we actually want to simulate. So the underlying goal itself is very similar as before, but what we learned over the past few years was that one could actually tailor the kinds of computation that you do on a quantum computer so that A, the effect of noise is much more benign than what you would naively expect, and B, a small quantum computer can potentially simulate a larger system with some extra side classical processing. So the reason why this is possible is kind of interesting, actually. So you can imagine, let's say you have a quantum computer. You can imagine all sorts of things that you can do with a quantum computer. You can run any gates that you want. And there would be a sort of a spectrum on what kind of things would be easier to do and what kind of things would be harder to do. By hard, I mean, you may need a larger quantum computer, or you need to run a computation for a very long time. And by easy, I mean you will need a smaller quantum computer, and also you'll need maybe a smaller number of gates. It turns out that if, for the purpose of creating a physical states of interest, for instance, like simulating the superconductivity, the kinds of computations that you do compared to other computations, such as optimization or machine learning, is much more benign. So one of the miracles is that in order to study the physics that we care about, the challenge of physics, it actually suffices to run a quantum computation that lies on the easier end of the spectrum. So that's one good news. And another good news is that there's some form of noise resilience that were somewhat unexpected. So what do I mean? So let's sort of like zoom in into this particular subset of problems that we care about, namely simulating physical systems, and let's just forget about everything else, okay? So now we move this thing into the center, and now we want to sort of like zoom this out. Good. And now you see that I have a different color scheme, and what this color scheme is supposed to represent is the susceptibility of the physical quantity of interest to noise. So there will be, again, a spectrum. Some of the things that you care about the system may be more susceptible to noise, so that the answer that you get will be more prone to errors. But maybe some of the things that you care about will be less susceptible to noise. And so maybe for those things, it's okay. Maybe we can like trust these devices. And the remarkable thing is that even though there are certain things that are obviously very susceptible to noise, such as, let's say, if you want to know the exact coefficients of the wave functions for all the coefficients, and it turns out that this is a very, very hard thing. And basically any form of non-negligible error will basically wash away your answer. However, if your goal is to study actual physical quantities that matter, such as, let's say, energy or magnetization or the superconducting order parameters, for the purpose of estimating those things, they're susceptible, they turn out to be actually much less susceptible to noise than what you would naively expect. So these are all theoretical results, I have to tell you, and while they are encouraging, these ideas have not been implemented on real devices yet. But the hope is that maybe we can actually implement these on the devices and indeed see that they are actually reliable. And moreover, maybe we can predict something useful about these challenging many-body physical systems that we didn't know about before. So the analogy that I want to make is that at the very beginning, people were a bit optimistic and thought that we have these very awesome devices. So maybe we can just plug in this device into every problem that we care about, and that device will magically output all the answers that we want. Now it's proving more and more that this is too optimistic, but still, in some sense, we're having a much more interesting story now. So now we're beginning to realize that these devices, it will be a very useful tool to study these systems indeed, but it won't be just this device alone that you need. You need all sorts of like interesting physical theories that I don't have the time to get into, that together with these devices and the theories that we hopefully, I think we'll be able to make some important progress over the next 5 to 10 years. So the summary that I want to make is the following. So like everyone in this field, both at University of Sydney and everywhere else in the world, whoever is working on quantum computing, we all have the same goal, which is to build a large-scale fault-tolerant quantum computer. And that's a very worthy goal, and we think we can do it. But there will be also other important physics along the way, which is encapsulated by this acronym NISQ. And I think there's plenty of opportunities. So, and you could be the one who writes this story. Okay. I'll leave it at that.
Thanks, Isaac. We've had a couple of questions in the chat. I'll ask you the first one. Can quantum computing be applied for gaming and VR applications when used with normal computers to enhance graphic and state creation?
So the short answer is I don't know, but I should mention that there are some, okay, so I haven't used VR to be honest, but I do know that in machine learning, there are these neural networks called convolutional neural networks. There are quantum versions of these convolutional neural networks, which appears to provide quantum advantage in certain regimes. Whether they can be actually useful in near term, this is less clear. It's an interesting question.
And we've got another question from Jake, which Stephen has already sort of answered on the chat. So we'll skip that one and go to the next one, which are, what are your views on using near-term devices to perform tensor network contractions? And do you believe that such devices could offer any useful advantages over classical machines, be it speed up or otherwise?
Oh, right. So actually, like what I was alluding to in these slides were precisely tensor network contractions. And I am very bullish on that because quantum computers are trivially better than, obviously better than classical computers that are classical computers are at contracting tensor networks, because that is precisely what the quantum circuit is about. But moreover, it turns out that for the purpose of contracting tensor networks that appears in physics, we have this extra bonus that they are noise resilient, meaning that naively, if you have, like, let's say n tensors, you would expect the noise would scale linearly with n. But if you get lucky, sometimes the noise does not scale with n. It just like goes up a little bit and then this stays the same way. So I think this is one of the more promising approaches for near-term quantum computing.
Okay, great. Thanks, Isaac. I'm going to jump in now and share my slides, but keep the questions coming and we can answer them in the panel session following my presentation. So I'm just going to share my screen now. Okay. So, hi everyone, my name's John Bartholomew and I'm a lecturer at the University of Sydney and I'm director of the Quantum Integration Laboratory, which is the newest laboratory in the quantum science group. And so Cornelius and Stephen and Isaac have done a great job in introducing the kinds of things that we're working with, and also have done a great job in I guess showing you some of the buildings that we have access to here at the University of Sydney. And so my lab will be in the University of Sydney Nanoscience Hub, but I'm just starting out. So we're going to be building up a lab, and I think the lab that Cornelius was showing is something to aspire to. So we'll be building up a lab with similar optics, but using a completely different system. And so the system that I'm interested in is using atoms which are in crystals. So we can use some of the same atoms as what Cornelius was talking about, but instead of trapping them with electrodes, we actually use the surrounding atoms in the crystal to trap them. And that has a lot of disadvantages, but also some advantages that we'd like to take advantage of. And so you can see a picture here of one of the crystals that I'm interested in. It looks like a diamond, and many people think it's a diamond, but it's not a diamond. It's actually a particular type of laser crystal, and Cornelius helped me take that photo earlier in the year. And so in my lab, the Quantum Integration Lab, we're interested in a number of quantum technologies, and probably not so specifically quantum computing. But rather trying to make connections between different quantum systems to make the quantum analogy of the internet. So I'll take you through a little bit of some of the things that I'm interested in. And if you're interested in talking more, please feel free to email me or get in touch. So the basic idea is that any kind of complex network requires some sort of memory or transduction. And so what do I mean by those two things? Memory is where we store information. So when I started my undergraduate degree, I was doing my assignments and storing them on floppy disks. So these only contain about 5 megabytes of data. And so you can think of it was going to be very difficult to do a number of the things that we do today if that's the only memory that we have access to. But obviously, if you can move on from that and use things like cloud-based memory services, then you open up a whole new range of opportunities. And these include things like very long-term storage and also being able to distribute resources. And so that's one of the main aspects that the internet gives us. On the other side, transducers are essential for these types of information sharing networks. And so a quick tour of what a transducer is if you want to watch a video like the one that we're recording now, or any kind of video from a server, that's usually stored as some configuration of magnetic or electronic domains in some physical system a long way away. And so what needs to happen is you need a transducer to convert that information into some kind of voltage that varies over time. And then you need to transduce it again. And if it's going through a fiber optic network, then that voltage needs to get converted into the intensity of light, which is varying as a function of time. And then at the other end of the fiber, it needs to get transduced back to a voltage again, and then ultimately into light and sound so that it interfaces with us, so we can hear and see what we're trying to watch. And so what these transducers allow you to do is to use application-specific hardware. So to use exactly the right tool for the right job. And so these are both memories and transducers are the types of things that we'd like to have in the quantum domain, but are technologies that are still under development. And so these ideas about the difference between the classical and quantum domain have already been introduced today. But we're going to look at them briefly here in terms of what does it mean for errors. And so in a classical system where we just have this 0 and 1, the only way that you can really get an error is if a 1 goes to a 0 or a 0 goes to a 1. But in the quantum domain, a qubit has a larger number or a larger parameter space. So errors can be that same error, so going from a 0 to a 1 or a 1 to a 0, the south to the north pole or the north to the south pole on this block sphere representation. But if the qubit, which is represented by some point on that sphere, moves around on the surface at all, then that is also an error. And physically what that translates to is that if we have our two qubit states, a 0 and a 1, which are separated by some energy gap, errors happen when these two levels move or the relationship between them changes. And so if the energy between them changes, as I'm showing here, that causes errors in our system. So all sorts of things can cause those errors, things like loss and gain, changes in polarizations, interactions with photons or vibrations, magnetic fields and electric fields. So quantum information is fragile because there are so many different ways in which it can be disturbed. And so just to give you an example of how that relates to the challenge of building a network, if I want to build an optical network, which is working at the quantum level, so say I want to send single photons in a network around Australia, loss is a key challenge. And the reason is because even though optical fibers are really good at distributing light, there's some finite loss, but that loss builds up exponentially over distance. And so I've shown here where the Sydney Nanoscience Hub is in Sydney in relation to the rest of Australia. And if I want to send a single photon to Canberra, then the chance of it actually getting to Canberra through an optical fiber is around 1 part in 10 to the 5. So 1 part in 100,000. If I want to send it to Melbourne, then that chance decreases even further, and it's about 1 part in 10 to the 12. If I want to send to Perth, then we're right down at only having a chance of about 1 part in 10 to the power of 46 of that photon making it through an optical fiber and getting to Perth. But in reality, if I was really wanting to do that, I wouldn't send it through an optical fiber, because once we get above a distance of about 400 kilometers, you're much better off transferring that photon by using a satellite. So bouncing the photon or sending the photon up to the satellite and having it emit back down to a different location. But if you do that, you're still stuck at about 1 chance in a million of the photon surviving. And so this loss in quantum networks is very detrimental. There's no way to amplify that signal back up without dramatically increasing the noise in these systems. So that's one of the challenges that I'm interested in solving. And so I use particular types of atoms that are held in crystals, and I try and make them into networks. And so to do that is trying to overcome the loss that we get in things like optical fibers. And so one way that you can think about doing that, and I work with some collaborators at the Australian National University, is that we have a system in which quantum information lasts for over 6 hours. And so what we thought of at the time was that we could send some light into a crystal and then ship that crystal over distance to get the light there and then recall it. And so that's just one of the ways that we're looking at building up this kind of technology in my lab. But there's more than just this quantum delivery service that we need to be interested in. So if I try and entangle or create quantum connections between 3 quantum systems, Q1, Q2, and Q3, there's a number of different elements I actually need to do that. I need some memory because sometimes one link will work and the other links won't. So I need to be able to hold on to that quantum information until I can get round to making the other links work. I also need some way to convert between different frequencies. So the quantum computers that Isaac was mentioning at Google, they operate in the microwave regime, so at low frequency, whereas optical networks use optical photons, which are at higher frequencies. And so if we want to pair up that type of technology over optical networks, we need a way to convert between those two without adding any more noise. So converters are another aspect that we'd like to have. Finally, at each of the quantum systems, we also need to have a bit of computing power to correct for any errors that happen along the way. And so what we're basically trying to do in my lab is to put all of those different components on a single chip. And so these include things like quantum memories, sources of entanglement, so things like entangled photon sources or single photon sources, ways to convert between microwave technology and optical technology, and also some recent work that we've been pushing into is looking at developing some computing power on these chips as well. And so all of those aspects are things that we're interested in the quantum integration lab. And so I'll stop there. But yeah, please feel free to get in touch. As I said, it's a group that's just starting out. So there's lots of opportunities for both undergraduate and graduate level projects. So thanks.
I think there's a question for you,
Yeah.
John, just showed up in the chat. So do vibrations during transit have any impact on the quality of the information that is stored within the crystal? Or is it really only vibrations within the lattice due to thermal excitations that would degrade the quality of the information?
That's a great question. And in fact, one of the main aspects that still needs to be tested in this idea. So what happens when you vibrate a crystal is that you actually apply a force to the crystal, and that force creates pressure changes and accelerations in the crystal. So at a macroscopic level, that actually interacts with the quantum states and can affect the information that you're storing. So the reason that I'm optimistic about this is because the states that they're storing the information in are very insensitive to those types of interactions, but it's something that needs to be measured. And so it's a really good question. One of the things we're interested in learning more about. Okay, so I've pulled the chat back up now so I can see that. I think unfortunately we've lost Stephen because he had to go to another meeting, but we've still got Isaac and Cornelius on the line. And so if you had any other questions that you wanted to ask, we're happy to answer them. So you feel free to unmute yourself and ask, or I'll post it in the chat. If people are a little bit shy initially, I actually have a question for Isaac and Cornelius that might get things going. So my question is, what did you study in your undergrad that you thought was useful for getting into the quantum information field?
Good question. It's not exactly what I ended up doing, but I actually, in my previous life, I worked in an ion trap lab, if you can believe that. So I was supposed to design the potential surface to trap the ion. And even though like this wasn't like exactly what I ended up loving, like it like sort of like helped me like venture into other stuffs that are like related directly. I guess like in my case, I learned that I am more of a theorist, but I think like starting something is important, and then you can like venture off and try out a bunch of things. But short answer, ion trap.
What about you, Cornelius?
Yeah, I mean, I actually didn't start in physics. I actually did international relations first, and then took the long way through computing, actually. So I've also done a degree in computing, and then went into physics. And so that was quite a long, windy road. But then eventually in physics, which I really was very excited about at the start, it took quite a while to find the way to quantum information in general, because there's so much interesting and exciting physics out there. And I guess one word of advice I would give is to make sure that you're absorbing as many of the tools as you can as you go through it. So that specifically applies to math. So that's something that we were sent to take lectures with the mathematicians, which weren't really tailored to the physicists. And so it was really hard, and lots of us really felt like, why are we doing this? And it's only later then, in later years, when you get to the applications, that you realize that, oh, this is actually quite useful. And so there's one example that I always like, and that's various actually. One of them being Bessel functions. You might just wonder, if you love mathematics, they're brilliant, they're beautiful. But then at some point, somebody might tell you, when you encounter maybe a fiber optic cable and you put light into that cable, that you're looking at Bessel functions, you're looking at solutions to a cylindrical object and a wave traveling through it. And then you tweak it and you can actually see them light up in patterns and in structures. And this is something, when you encounter that the first time in the lab, it's almost like a revelation. And so that's also how I came into this. I took up some optics first, and through optics came to atomic physics. And then from atomic physics, how to use these things then to make quantum computers to quantum information. So it was a longer road, but it was a very exciting one. And now I'm really excited to be in that field.
I'll add one thing from myself, which was I had to fill one unit in my first year of undergraduate. And I took a computer science course and learned how to code. And so for me, that was by far probably the most important course I ever took, because everything we do in the lab, everything we do to process the data is all through computer programming. So that was one thing for me, which was really valuable. A related question from the chat was, did we know what we wanted to be when we started out as undergraduate students? So I guess people have already touched on that, but if there was anything to add for myself, I didn't know. I knew that I went into university not really even sure that I wanted to be a scientist. I was also interested in a lot of other topics, and it wasn't until sort of doing some projects with people and working through the different subjects that physics really crystallized. I had always been interested in physics, but yes, no, I didn't know for sure.
I think
it's pretty much the same year. Yeah,
I guess I always wanted to do physics since I was young, so like that was an easier choice for me. But like precisely what I do in physics, like that took some soul searching.
Yeah, and I think just to add to that, what Isaac was saying, just figuring out in physics, right? We have this divide between theory and experiment. Where you fall, and also there's an in between where you've got an overlap with both. So I've got a number of colleagues who went on and did a theory project, for instance, for their honors, and then went on and did an experimental PhD, or the other way around. So you do have these examples, and I guess that's one thing that's very useful. Just go ahead and try. Do a project with a theory colleague, do a project in the lab, and see what you like. you really need to try it out. So this is, I think, the takeaway that I got from that. Yeah, and I think so that was a question from Jake, and there's another one. Maybe, Isaac, do you want to take on the question about information transfer?
Yeah, I think I've answered this question many times, actually. So, so the question is, does the information transfer between two entangled particles exceed the speed of light, as in, is it instantaneous? The short answer is no. And so just to be clear, if you have entanglement, you can boost the communication capability in a sense that, well, like, let's say you have an entanglement, and let's say let's say you could send like 1 bit at a time before you had entanglement. Like with entanglement, you can send like 2 bits at a time. But like fundamentally, so you can change the rate at which you send the information, but you cannot change the absolute speed of the information transfer. Let me just see if what the remaining part of the question is. If so, what are the consequences in relativistic constant? Or does this not apply since it's an immaterial transfer of information? I would say it's the latter. So the quantum mechanics and relativity, there's no contradiction whatsoever.
I guess there's another example one can give, and that's quantum communication, where people always ask this question when it comes to that. So when we share entangled states and then we measure. So for instance, what you would do is you would take a photon, you would send it through a crystal, and you would get out 2 photons which are entangled, and then you take your entangled photons and put each into a fiber optic cable and bring it out to remote parties. So now they're very far away. They each received a particle that is part of this entangled set, and now they can make a measurement. And so there's this spooky action at a distance that Einstein was referring to, because he didn't really like that at all. And that is, you make a measurement here, and it instantaneously, that's probably what you were referring to, and that question affects the outcome here. But there's one little tricky bit to it. When you measure the outcome of, you measure the outcome of a measurement of a quantum system is random. So that means the party number 1 here may have measured, and obviously things happened here simultaneously. So, but they are getting a random list of information. So you can't force a measurement to be one or the other. You're getting a random answer. There can be a likelihood that one's more likely than the other, but it's still random. And so in order to then establish information transfer between the 2 parties, you actually need to talk. You need to communicate over non-quantum lines. You need classical information to travel, and that, alas, is always speed limited. So even though you have these correlations being instantaneous, there's no way to transfer information.
Yeah, so I think we're going to try and wrap things up at about 4:15. So if you have any other questions, feel free to ask them. There's none popped up on the chat so far, so I'm going to ask Cornelius and Isaac another question. What are you most excited about in the quantum computing or the quantum information field right now?
Yeah, I think, so for me, there are actually 2 things that I'm very excited about. I mean, one was the goal that Isaac and also Stephen talked about, that's building this fault-tolerant machine using active error correction. That's also something that we investigate in the lab. So how do you make these physical qubits perform together in a way where you can get a fault-tolerant qubit, so one that doesn't just break all the time, but one that actually gives you reliable functioning, but then will just be at one logical qubit. But the beautiful thing in this field is that on the way to this logical qubit, we need to develop so many techniques, and lots of it is not necessarily quantum. It's actually classical computing. We need very fast classical computing, low latency. For instance, when we do error correction, we learn about an error, what's called an error syndrome. So something has gone wrong. We read out a syndrome that tells us something went wrong, and now we need to interpret the syndrome and then correct the error. But that needs to be fast, because quantum information is fragile. So the longer you take, the more errors could sneak in. So you really need to be fast. And so this triggers a whole lot of development of classical electronics, new optics that need to be engineered and all that. And with that, in turn, in this NISQ era that Isaac was talking about, where you have not a fault-tolerant system, but you have lots of semi-faulty, but maybe relatively good qubits, but not perfect qubits. If you had these new techniques and you combine those 2, new applications emerge. And so, for instance, as I was talking about this magnetism, so when you take a NISQ system, which is not error corrected, but you're measuring a quantity like energy, for instance, or magnetization, these are the things that we can do in the lab already now. And it turns out there's one experiment with trapped ions with the group of Chris Monroe, where they did this with 50 ions, and you can explore a regime where you cannot calculate classically what the outcome would be. And you can already access these regimes now. So I'm quite excited about quantum simulation and using those pre-fault tolerant devices to learn answers to questions in physics and chemistry.
Yeah, I would agree with that, obviously. One thing that I would add is that I just want to reemphasize is that now we're going to have devices where theorists will have no idea what to expect. And that's this was not the case before. All the quantum computing devices previously, whatever people built, theorists could sort of expect what was going to happen, more or less qualitatively. But now you have more than 50, let's say 100, there will be certain questions that theorists just won't know how to answer. And the experimentalists will provide some very concrete data. And from that, that's usually the beginning of a new theory, if you look back at the history of physics. So I think that's the unknown is actually very exciting to me as well.
Yeah, I think
John, what about you actually?
Yeah, I was going to say, well, I think they're both really, really great perspectives and similar to my own. I think for me, one of the most exciting things is the maturity that you're talking about. So the quantum systems that people envisaged, these small quantum systems that people were hoping to build, 10, 20 years ago are now here. And so you can start using them for a whole different range of applications. And I think the exciting thing is that new science is going to come out of that. The other thing that I'm really excited about is that the quantum aspect of our work is now becoming broad enough that it's not just the regime of people who are into hardcore physics. There's a lot of tough problems that we're going to need to solve, which are going to need all sorts of expertise. So that's chemistry, physics, engineering, computer science. All of these aspects are going to be important as we build up to these larger and larger systems. I'm obviously I'm in the field, so I'm a bit biased, but I think the future is really exciting for the field. I think all of us are reading the next question in the chat. We can probably take this one as the last question, but if anyone has any more questions, please feel free to reach out to us on email. Any of the professors or staff in the quantum science group would be more than happy to answer your questions on email. So please feel free to reach out. I'm going to post some more links in the chat just before we go. So I don't know whether Isaac or Cornelius, if you wanted to tackle that final question in the chat.
Mm-hmm. Oh. Right. So the question is, how confident are we that quantum mechanics as we know it, aka Copenhagen interpretation, is a sound basis for the development of quantum computers? So insofar as the size of the quantum computer, by which I don't mean the physical size, the number of qubits is large, but not larger than human size, then I think we have no reason to believe that the Copenhagen interpretation would be valid in that regime. So if you have quantum computer that's planet size, that will be a different story. I think there are some questions there, but at least for moderate sized quantum computing, I don't think there's people seriously doubt about this.
Yeah, and I think just going there to, as I read Copenhagen interpretation, I guess there's the question about what is wave function collapse? Is there many worlds theory? What's really the right understanding about quantum mechanics? And I think One division that, or one thing that one should look at there is what is this question about? So this is really, it's a fundamental question. It's about more or less, you could say even philosophy to some degree. And in the field, this is called quantum fundamentals. So these fundamental quantum questions are being treated at separate conferences where people ponder, what's the meaning of it, and does the wave function really collapse? And then sometimes dedicated experiments are performed, often with photons. But the people that do quantum computing, that try to build these devices, admittedly, we don't really think about this very often or very much at all. So we're building these devices, and all the tests and the things that we do have basically pointed to quantum mechanics, to the description being correct that we're using. But we're also, not exploring all of that these fundamental questions touch upon. We're just trying to build that small device, if you will. And so I think that's how I would answer that. And I think there's the question about getting a copy of these slides. I believe we've recorded the meeting, so there'll actually be a recording of this posted.
Yeah, okay. I think we should call it there. But thanks to everyone for coming along today and listening. And yeah, hope to talk to you more in the future.
Thanks for coming.